So I wanted to look at our discussion of conditional probability. We saw yesterday that the probability of A given B is the probability of both A and B over the probability of just that given B. And we looked at using a Venn diagram for that, but I want to look today at using a tree diagram for this, because this is the type that you really couldn't use a Venn diagram for. And it's a kind of thing where we've got two different kind of decisions that are made, or two different aspects to a problem. And theoretically there could be more than just two, but we'll keep it at two just to keep it simple. All right? Now the problem here says that we have the top shelf in a cupboard that contains 3 cans of pumpkin soup and 2 cans of chicken soup. All right, so we've got 2 shelves, all right, and we have 3 cans of one kind of soup and 2 cans of another kind of soup. And then it says the bottom shelf contains 4 cans of pumpkin soup and 1 can of chicken soup, all right? Has anyone actually had pumpkin soup? I know it's a thing, but you've had it? All right. So, maybe if you put made it taste like pumpkin pie or something, but, I don't know. Anyways, we look at this and it says Lucas is twice as likely to take a can from the bottom shelf as he is from the top shelf. Suppose he takes 1 can of soup without looking at the label. Determine the probability that it's chicken, and then determine, if he realizes it's chicken, determine the probability it was taken from the top shelf. Right? That's what part B is saying. It was taken from the top shelf given that it's chicken. So here we're looking for the probability of C. Here we're looking for the probability of the top shelf given that we know it's C. Okay, now we essentially have 2 decisions that are made. The first decision is which shelf are we going to pick it off of, okay? So first of all, why is it not writing? Try this again. Just write like this. Doesn't like that one spot for some reason. Which shelf?
Try scrolling.
There. Not sure why it didn't like that, but okay. So I should spell it correctly too. Which shelf? There we go. All right. So it says that he's twice as likely to take a can from the bottom shelf as he is from the top shelf. So as we construct a tree diagram, we have 2 choices: the top shelf and we have the bottom shelf. Now it doesn't tell us the probabilities directly, but indirectly it does by saying we're twice as likely to choose off the bottom shelf. It's more convenient, it's easier to reach. Alright, so what would the probabilities have to be in order for that to take place? Think. You have 2 options. In order for one to be twice as likely as the other, what would the 2 probabilities have to be?
So what was there?
There we go, 1/3 and 2/3, okay? So the probability of picking the top is going to be 1/3, and the probability of picking the bottom is 2/3. All right, do we understand that? We got the thirds, just, you have to kind of think through this logically. In order for two things, you have two options and one to be twice as likely as the other, you kind of need three parts to it. You know, he's going to have one part, he's going to have two parts. So that's thirds then. So it's 1/3 and 2/3. Kind of just thinking about it proportionally. Okay? Any other questions? Okay. Now, after we look at which shelf, we then need to consider which can or which kind of soup is he choosing. Okay? So which soup? So here's where we have to pay attention to details from the problem, okay? Because it says on the top shelf we have 3 cans of pumpkin and 2 cans of chicken. So what's the probability of picking pumpkin soup off of the top shelf? It's 3/5. Okay? By the way, sometimes you'll see these probabilities written like I have them here. Sometimes you would see it written like on the little branch of the tree. Okay? It means the same thing. I like writing them at the end, but that's just preference. Now, what's the probability of getting chicken soup? 2/5. Okay? 2/5. Well, then we have the same choice for the bottom. Okay? What's the probability of getting pumpkin off the bottom shelf? 4/5. 4 out of the 5 cans. And then the probability of getting chicken off the bottom shelf? 1/5. Okay? 1/5. Now, it's going to be important to pay attention to notation as you work your way through these, because one of the things that we're going to consider is some combined probabilities like we've looked at earlier, okay? At the end of each of these branches of our tree diagram, we actually have a combined probability. Here, if we pick the top shelf and then pick pumpkin, that's going to give us the probability of top shelf and pumpkin. And how would we find that probability? Multiply or add? We're going to multiply, okay? We have one decision followed by another. It's kind of like our fundamental counting principle, all right? This is how many ways, 1 out of 3 ways that we could pick the top shelf, and then 3 out of 5 ways we could pick the can of pumpkin. So 1/3 times 3/5 is going to be 3/15 or 1/5. Okay? If we're giving a final answer, we'd reduce, but you'll see in a sec why I didn't. Okay? So now we can do this with all 4 of these branches of our tree diagram. Okay? What's the probability that we had the top shelf and we picked chicken? What? 2/15. 1/3 times 2/5 is 2/15. Okay? Now we'll do the same thing for the bottom shelf. All right, we have the probability that we pick the bottom shelf and pumpkin. So it's 2/3 times 4/5. Okay, so we have 8/15. And then finally, the probability we pick the bottom shelf and we pick chicken. We've got 2/3 times 1/5. So we have 2/15. Now notice I didn't reduce this one because now we can see they're all 15ths. Right. Now pay attention to what should add up to 1 here. Okay? Each of these decisions, your probabilities ought to add up to 1. 1/3 and 2/3, 3/5 and 2/5, 4/5 and 1/5. Okay? Each of those pairs ought to add up to 1. When you do the combined probabilities at the end, all 4 of them ought to add up to 1. Okay? So, 3 and 2 is 5, plus 8 is 13, plus another 2 is 15/15ths. We have everything covered. Okay? So, any question on how we filled out the tree diagram? Okay. But by the way, you're always going to multiply, the 1/3 times the 3/5. Okay? Now, there is some adding that we'll do. Okay? You'll notice part A here says, what's the probability that we get chicken? Well, there's 2 different ways we could get chicken. We could get chicken off the top shelf, or we could get chicken off the bottom shelf. So in order to calculate what's the probability that we get chicken, we need to consider the probability of going on the top shelf to get chicken and the probability of going from the bottom shelf to get chicken. Okay? Notice we already figured out what both of those were. Top shelf and chicken is 2/15. The bottom shelf and chicken is 2/15. So total, we have a 4/15 chance of getting a can of chicken soup. Yes, Alexi?
You cannot the top. Never mind. I was looking at geography.
Okay. Any other questions? All right, now, what's the probability of picking a can of pumpkin soup?
11.
How'd you get that, Rachel?
We just added the 315 plus 8.
Okay, good. To get the probability of getting pumpkin soup, we could have gotten that off the top shelf, or we could have gotten that off the bottom shelf. So, like Rachel said here, we've got 3/15, which is up off the screen, plus 8/15. So we've got 11/15. How else could we have gotten that?
1 minus 4/15.
Very good. Getting pumpkin is the complement of getting chicken, so you could subtract from 1. Either way is totally valid. Okay. So we've answered our first question. We wanted the probability of getting chicken. We answered more than just that. But now we can answer part B. Okay? Part B, what's the probability it was taken from the top shelf given that it was chicken? All right? So in other words, like we said, it's the probability of T given C. So here's the thing, we just blindly reach and we grab a can and we look at it and it ends up being chicken. Okay, where did it come from? Or probably better, because we could probably feel where it came from. We just ask someone to grab one for us and they hand it to us and it's chicken soup. Which shelf did they get it off of? Okay, well this is, here we can figure out the probability of that it came off of the top shelf. Alright, what is our formula for this conditional probability?
The probability of P and C over probability of
Over probability of
C.
C. Okay? And notice, again, we've already figured out what these probabilities are, we just need to plug them into the formula. Okay? So the probability of T and C was what? It was 2/15. So 2 out of 15. The probability of getting chicken at all is 4/15. So that reduces to 1/2. Okay? If you think about it, this will make sense. Okay? You were twice as likely to pick the bottom shelf, but once you got to the shelves, okay, you were twice as likely to pick the bottom shelf over the top, but once you got to the shelves, the chicken was twice as likely to on the top shelf as it was on the bottom. So it kind of evens it out. Twice as likely and half as likely, you have an even chance, 1 out of 2. That came from the top shelf or the bottom shelf. And you might think, okay, this is kind of a ridiculous example. And you're right, it is, okay? The fact though is it's a very simple example that can be applied to a lot of other significant situations, all right? When companies will do drug trials or they'll do a test for a disease particularly is one case where this can be used. All right, you're running this test, and almost any time a doctor runs a test, there's a possibility that the person who's getting the test done on them could not have that disease, but the test comes back and says that they do. We call that a false positive. All right? And then, depending on what kind of disease you're testing for, that could cause a lot of nerves and anxiousness over nothing, because it turns out they're not sick after all. Okay? On the other hand, it's also almost every test that's run, it's possible for someone to have a disease, but the test misses it. Okay, the test comes back and says that they don't. All right, the key is, if we were researchers developing a new test, we would want to try to minimize the percentage of false positives, obviously, and we'd want to minimize how many people we missed with this test as well. Okay, but what we have is a case where we could look at all of the positive results. Okay? We could look at all the positive results for this test and then go back and say, okay, what's the probability that someone who gets a positive result actually does have the disease? In other words, it was testing it correctly. And what's the probability that someone who gets a positive result actually does not have the disease? Okay? And that's a significant thing to figure out, because if 1 out of every 4 person that your test is saying has this disease really doesn't, okay, then you're causing a lot of people a lot of anxiousness over nothing. Okay? you would want to have that percentage much lower. And I'm sure they have standards or whatever for what it would have to be in order to actually use that test on a large scale. Okay? Also, think about not just, scaring people unnecessarily, but think about, what kind of treatment might get started. If this is a cancer test or something, are we putting people on chemotherapy or radiation unnecessarily? Obviously that would be really bad. Or we're putting people on medications that have a lot of harmful side effects. And it turns out that they didn't need to be on those medications in the first place. Those are really important decisions that we have to make, and these are calculations that can be used to determine how good a test for that kind of disease would be. All right. So that's just one case. I told you yesterday to hold off on these. I gave you 3 different problems. This first one you can do with just the Venn diagram, but these other 2 can be done with, or need to be done with this tree diagram, okay? So, I'm going to have you finish those for Thursday, okay?